Chapter 7: How Web Applications Work and Building a Secure Foundation. In this chapter, our main learning objective is applying security strategies to the web application creation. That includes the software development lifecycle and coding practices. Core concepts are going to be how a web app functions, standards for web apps, how to design and build a secure and compliant web app as well as website, and best practices to mitigate risks for websites and applications. We're introducing the fundamental idea of how web applications actually work behind the scenes. Most people use web applications every single day. Online banking, learning platforms like Canvas, shopping on Amazon, or collaborating in Google Docs, but rarely stop to think about what is happening when they click a button or submit a form. A web application is different from a static website because it processes user input. A static website mostly displays information. A web application, however, reacts to what you do when you log in, upload a file, search for a product, or submit an assignment. The application is actively handling and processing data, not just showing content. At a high level, web applications operate using what's called a client-server model. The client is your web browser, such as Chrome, Firefox, or Edge. The server is a remote system that stores the application's code, databases, and business logic. When you enter information into a web application, your browser sends a request to the server. The server receives that request, processes it, often by checking permissions, validating input, or querying a database, and then sends a response back to your browser. That response might be a web page, a confirmation message, or updated data on the screen. A real-world example of this is online banking. When you check your account balance, your browser sends a request to the bank's server. The server authenticates who you are, looks up your account information in a database, and then sends your balance back to your browser. This entire exchange usually happens in milliseconds, but every step in that process matters from a security standpoint. This constant back and forth communication is exactly why web applications are a major target for attackers. If developers misunderstand how requests, inputs, and responses work, vulnerabilities such as SQL injection, cross-site scripting, or broken authentication can occur. Understanding how web applications function at this basic level is the foundation for everything else in this chapter. Before you can secure a web application, you must first understand how data moves through it and where things can go wrong. This slide highlights an important distinction. Not all websites are web applications. A simple website is mostly static. It displays information like a restaurant menu or a company's About Us page. There's little to no user interaction beyond clicking links. The server sends the same content to everyone. A web application, on the other hand, responds differently based on who you are and what you do. It processes input, makes decisions, and often interacts with databases or other services. Think of a college website versus Canvas. The CSN homepage shows the same content to everyone. That's a website. Canvas changes based on your login, your courses, your grades. That's a web application. From a security perspective, this distinction is critical. Static sites have fewer attack surfaces. Web applications, however, must handle logins, permissions, data validation, and session management. Every one of those components can introduce vulnerabilities if not designed correctly. When attackers breach systems, they're almost always targeting dynamic behavior, not static content. That's why secure coding practices matter far more for web applications than simple informational websites. This slide breaks down the functional components of a web application. First, we have the front end, which runs in the user's browser. This is built using HTML for structure, CSS for styling, and JSVP for interactivity. The front end controls what users see and how they interact with the app. Second, we have the back end, which runs on the server. This is where the real processing happens, handling logins, validating input, querying databases, and enforcing security rules. Back-end technologies might include PHP, Python, Java, or JavaScript with Node.js. A useful real-world analogy is ordering food online. The menu and buttons you see are the front end. The kitchen that receives your order, checks inventory, and prepares the meal is the back end. If the kitchen fails or is compromised, the whole system breaks. From a security standpoint, one of the biggest mistakes developers make is trusting the front end. Attackers can manipulate browser-side code easily. That's why all critical security checks must occur on the back end, regardless of what the front end allows or restricts. This slide shows a simple HTML example, but it's incredibly important conceptually. What you're seeing here is client-side code. HTML that creates headings, images, links, and text. This code runs entirely in the user's browser and is fully visible to anyone who views the page source. Even though this example looks harmless, it demonstrates a key security principle. Anything running on the client side cannot be trusted. For example, imagine this page included a form asking for a user's name or age. A developer might assume users will enter valid data because the page looks controlled. But attackers can modify requests, bypass form restrictions, and inject malicious input. A real-world example is form validation. If validation only happens in JavaScript, an attacker can disable it and submit dangerous data directly to the server. That's how vulnerabilities like SQL injection occur. This is why secure web applications treat client-side code as a convenience, not a security control. Every input must be validated, sanitized, and verified on the server before it's trusted. Web applications provide several major advantages that explain why organizations rely on them so heavily today. First, web apps do not require installation on the client machine. Users simply open a browser and access the application. This means no software distribution, no version mismatches, and no local disk space requirements. A real-world example is Google Docs. There is nothing to install, yet users can create complex documents from any device. Second, maintenance is centralized. When developers update a web application, the changes happen on the server and are instantly available to all users. Contrast this with desktop software, where every user might need to download and install updates manually. Third, web applications are platform independent. Whether you are using Windows, Mac OS, Linux, or a tablet, the same application is available. This is critical for organizations with diverse users, such as universities, banks, or global companies. From a security perspective, centralized control also allows faster patching of vulnerabilities, assuming the organization actually applies updates promptly. Despite their benefits, web applications also introduce challenges. User acceptance can be a problem. Some users are uncomfortable with cloud-based systems or distrust web platforms. This is common in organizations transitioning from legacy systems. Browser compatibility is another issue. Developers must ensure applications work across multiple browsers and versions. A feature that works in Chrome may fail in Safari or an older version of Edge, potentially creating security or functionality gaps. Performance is also a concern because web apps rely on network connectivity, latency, bandwidth limitations, or server overloads can slow performance. For example, during online registration or ticket sales, systems can become unresponsive under heavy load. We're focusing on a key disadvantage of web applications: application problems and support complexity. While web applications offer convenience and accessibility, they are also built on multiple interconnected layers, often managed by different teams or even different organizations. When something goes wrong, identifying who is responsible for fixing the problem is not always clear. From the user's perspective, the situation is simple. The application appears to be broken. However, behind the scenes, diagnosing the problem can be far more complicated. For example, imagine a student trying to submit an assignment in a learning management system. If the submission fails, the issue could stem from many different sources. It might be a browser compatibility problem, a front-end JavaScript error, a back-end server outage, a database failure, or even an issue with a third-party service, such as cloud file storage or authentication. To the student, all of these look identical. The assignment didn't submit, but technically each cause requires a very different solution. This layered architecture makes troubleshooting slower and more complex. Support teams must determine whether the issue lies with the application developer, the organization operating the website, the hosting provider, or an external vendor. Each handoff between teams adds time, increases downtime, and often leads to user frustration. Another major challenge is that users have little to no control over web application problems. Unlike desktop software, users cannot reinstall the application, apply patches, or change system configurations. They must wait for the organization responsible for the application to identify and resolve the issue. This lack of control becomes especially problematic in time-sensitive environments such as online exams, financial transactions, or healthcare systems, where even brief outages can have serious consequences. From a security perspective, application problems introduce an additional risk. Performance issues, error messages, or service outages may be dismissed as routine technical glitches when they are actually indicators of an attack. For example, a denial of service attack may initially appear as normal slowness, or repeated errors may signal exploitation attempts. If monitoring and incident response processes are weak, these warning signs can be overlooked, allowing attacks to continue undetected. In short, while web applications provide flexibility and ease of access, they also introduce support, accountability, and security challenges. Understanding these app-level problems highlights the importance of clear ownership, strong monitoring, proper documentation, and well-defined incident response planning and secure web application design. Third-party applications are software components not developed entirely in-house. Web browsers like Chrome, Firefox, Edge, and Safari are all third-party applications that web apps depend on. Email clients, antivirus tools, and plugins also fall into this category. A key security concern is trust. When organizations rely on third-party tools, they inherit the risks of those tools. A vulnerability in a browser extension or plugin can compromise an otherwise secure system. This is why organizations carefully control which third-party tools are approved and regularly update them. Add-on applications introduce additional complexity. If an app is approved by a site publisher, such as a social media integration, it becomes part of the application ecosystem. Unofficial app stores are especially risky. While they may offer convenience, they also distribute malware or compromised software. This is why security professionals emphasize downloading software only from trusted sources and keeping anti-malware tools updated. We're focusing on a very common and important concept in modern web applications, applications that connect to other applications. Most web applications today do not operate in isolation. Instead, they rely heavily on third-party services to perform specific tasks. These connections are typically made through application programming interfaces or APIs, which allow different applications to communicate and exchange data in a structured way. Common examples of this include single sign-on services, payment processors, and cloud storage platforms. Rather than building these complex systems from scratch, organizations integrate existing services into their applications. An example is a website that allows users to sign in using Google or Microsoft credentials. The website is not managing usernames and passwords itself, instead relying on an external authentication provider to verify the identity. Another example is an e-commerce site that uses a third-party payment processor, such as Stripe or PayPal, to handle credit card transactions. These integrations offer major advantages. They reduce development time, improve reliability, and allow organizations to use specialized services that are designed and maintained by experts. From a business perspective, this makes applications faster to build and easier to scale. However, these benefits come with security trade-offs. When an application connects to another app, it becomes dependent on that external service. If the third-party service goes offline, changes how its API works, or experiences a security breach, the primary application may also fail or expose sensitive data. Even if your own application is well designed and secure, a vulnerable third-party connection can become an entry point for attackers. Security is especially critical at these integration points. Applications must authenticate to each other properly, limit what data and actions are allowed, and monitor activity for abuse. Poorly protected API keys, overly broad permissions, or missing logging can allow attackers to exploit these connections without being detected. From a security standpoint, attackers often target APIs directly because they can bypass the user interface entirely. If API security is weak, attackers may access or manipulate data without ever interacting with the application's front end. In summary, third-party app connections are powerful tools that enable modern functionality, but they also expand the attack surface. Secure web application design requires careful vetting of third-party services, strict access controls, secure API management, and continuous monitoring of all app-to-app interactions. At this point in the chapter, we shift from individual components to broader development strategies. When organizations decide to build an application, one of the first decisions they must make is what type of application to develop. A native application is built specifically for one operating system or platform, such as iOS, Android, or Windows. These apps are installed directly on the device and can tightly integrate with hardware features like cameras, GPS, and biometric sensors. A real-world example is a banking mobile app that uses fingerprint or facial recognition. From a security perspective, native apps benefit from platform-level protections, but must be updated frequently to address vulnerabilities. A web application, by contrast, runs entirely in a browser. Examples include Canvas and Google Docs. Web apps are highly accessible and platform independent, making them ideal for large, diverse user populations like universities or businesses. However, because they are internet-facing, web apps are constantly exposed to attackers and must be secured at every layer. A hybrid application combines elements of both. Many modern apps use a web interface wrapped inside a native shell. While this reduces development time, it also increases complexity and risk because both the native layer and the web layer must be secured. Here we introduce two foundational architectural models. With server-side rendering, the client sends a request and the server dynamically builds the page before sending it back. This model allows personalization and dynamic content, such as dashboards or account pages. However, it also means that user input is constantly being processed by the server, increasing the risk of injection attacks if validation is weak. Static site generation takes a different approach. Pages are built ahead of time and stored on a content delivery network. Because there is no dynamic processing for each request, static sites are faster and generally more secure. This is why many organizations use static sites for marketing pages while reserving dynamic architectures for authenticated areas. An example is an e-commerce site. Product descriptions are static, but checkout and account management are dynamic. Slide 15. We're comparing two different web application architectures: server-side rendering, shown on the left, and static site generation, shown on the right. Understanding this comparison is important because architectural choices directly affect performance, scalability, and security. Let's start with the left side, the traditional server-side rendering or SSR architecture. In this model, the client, meaning the user's browser, sends a request to a web server. That web server forwards the request to an application server, which processes logic, interacts with a database, and dynamically builds the page. The fully rendered page is then sent back through the web server to the client. This approach allows for highly dynamic, personalized content. For example, when you log into a banking website or an online learning system, the page you see is generated specifically for you. However, every request requires server-side processing. From a security perspective, this means user input is constantly being handled by back-end systems, increasing the risk of injection attacks, authentication flaws, or data exposure if validation is weak. Now let's look at the right side, which represents static site generation, or SSG, commonly used in newer website architectures. In this model, pages are generated ahead of time and stored on a content delivery network, or Canadian dollars. When a client requests a page, it is delivered directly from the CDN without needing real-time processing by an application server. This approach significantly improves performance and scalability because servers are not rebuilding pages for each request. It also improves security by reducing the attack surface. Since there is no dynamic code execution for most requests, attackers have fewer opportunities to exploit back-end vulnerabilities. However, static sites are not always sufficient on their own. That's why you see services on the right side of the diagram. When dynamic data is needed, such as submitting a form, logging in, or retrieving personalized data, the client communicates with back-end services through APIs. In practice, many modern applications use a hybrid approach, combining static content for speed and security with back-end services for dynamic functionality. The key takeaway from this slide is that architecture matters. Choosing between SSR and SSG is not just a design decision, it's a security and risk management decision that shapes how exposed your application is to attackers. Single-page applications load once and then dynamically update content using JavaScript. This creates a smooth user experience, similar to a desktop application. Examples include Google Maps and GitHub. However, SPAS rely heavily on APIS to retrieve data, which means attackers often target APIS directly. If authentication or authorization is misconfigured, attackers can bypass the user interface entirely. Progressive web apps blur the line between web and native apps. They can work offline, send notifications, and be installed on devices without app stores. While convenient, PWAS expand the attack surface and require careful permission management. APIs are the backbone of modern applications. They allow different systems to communicate efficiently without exposing internal logic. A useful real-life analogy is ordering food through a delivery app. The app doesn't cook the food. It sends structured requests to restaurants and receives structured responses. The API enforces rules about what can be requested and how. From a security standpoint, APIs must enforce authentication, authorization, rate limiting, and input validation. Many modern breaches occur not through the web interface, but through exposed or poorly secured APIs. We're breaking down how an API actually works step by step. While APIs often sound abstract, this process happens constantly behind the scenes whenever applications communicate with each other. Let's start with step 1. An application running on the client, such as a web browser, mobile app, or desktop application, issues an API request. This request tells the API what action it wants to perform. For example, a mobile banking app might request an account balance, or a shopping app might request product availability. The API then formats this request into a Uniform Resource Identifier, or URI, which is sent to the web server. This URI includes important components such as the requested action, headers that describe the request, and sometimes a body containing additional data. At this point, the API is acting as an interpreter, translating the client's request into a format the server understands. Now let's move to step 2. The web server receives the URI and evaluates it. If the request is valid, authorized, and can be processed, the server gathers the requested data. This may involve querying a database, calling another service, or performing business logic. Once the data is collected, it is packaged into a response and sent back through the API. This step is especially important from a security standpoint. If authentication, authorization, or input validation is weak at this stage, attackers may be able to retrieve data they should not have access to. Finally, in step 3, the API extracts the data from the server's response and passes it back to the client application. The client then displays the information or uses it to complete an action, such as showing search results, confirming a transaction, or updating a user profile. A useful real-world analogy is ordering food through an app. You place an order, the system communicates with the restaurant prepares the food, and the confirmation comes back to you. You never interact directly with the kitchen. The API manages that communication. The key takeaway from this slide is that APIs are powerful communication bridges, but they also represent a major security boundary. If APIs are poorly secured, attackers can bypass user interfaces entirely and interact directly with backend systems. That's why API security, authentication, authorization, logging, and rate limiting is critical in modern web applications. Security is not optional. Organizations are legally required to protect certain types of data. For example, universities must protect student records, healthcare providers must protect medical data, and online retailers must protect payment information. Compliance frameworks define minimum acceptable security practices, not best case scenarios. Failure to comply can result in fines, lawsuits, loss of trust, and operational shutdowns. At this stage in the chapter, we move from technical design into the legal environment that governs web applications. Internet law, sometimes referred to as cyber law, does not exist as a single unified body of rules. Instead, it is a collection of laws drawn from many traditional legal areas, including privacy, contracts, commerce, taxation, and intellectual property. One of the most important concepts to understand is that the internet has no physical borders, but laws do. A web application hosted on a server in the United States may still be subject to the laws of another country if it collects data from users in that country. For example, if a US-based website allows European users to create accounts, that website may be legally required to comply with European data protection laws. This creates a challenge for developers and organizations. legal compliance can no longer be treated as an afterthought. Security features such as consent notices, data retention policies, and access controls must be built directly into the application. In many cases, failing to comply with Internet law can be more damaging than a technical breach, resulting in fines, lawsuits, or forced shutdowns. Internet and web governance can be understood through several overlapping categories. The first is architecture, which refers to the technical structure of networks and systems. The way a web application is designed can either enable or restrict certain behaviors. For example, encryption architecture determines whether data can be intercepted or protected. The second category is laws, which define what behaviors are legal or illegal. These laws are typically written by governments and enforced by courts or regulatory agencies. A major challenge arises when laws conflict across jurisdictions. The third category is norms, which include cultural expectations and social standards. What is acceptable content or behavior in one country may be offensive or illegal in another. Web applications operating globally must account for these differences to avoid conflict and legal exposure. Censorship is a major issue affecting how web applications operate worldwide. Some governments heavily restrict access to certain types of content, including political speech, social media platforms, encryption tools, and news sources. For developers and organizations, censorship introduces both technical and ethical challenges. Technically, applications may need to implement region-based filtering, content moderation systems, or access restrictions. Ethically, organizations must decide whether complying with censorship laws aligns with their values. A real-world example is social media platforms that must alter or remove content depending on the country in which users are located. Failure to comply with censorship laws can result in the application being blocked entirely within that region. We're narrowing the discussion of censorship and control to a very practical area: web marketing and online advertising. While censorship is often associated with political content or social media, it also plays a major role in how products and services can be promoted online. Many countries, and even individual U.S. states, impose strict legal restrictions on advertising claims made on websites. These laws are designed to protect consumers from misleading, deceptive, or manipulative content. For web application developers and organizations, this means marketing content is not just a business concern. It is a legal and compliance issue. The restrictions listed on this slide highlight several common violations. First, false or unfounded statements about a product or service are prohibited. This includes exaggerating capabilities, making unsupported comparisons to competitors, or implying features that do not exist. For example, claiming that a software product is unhackable or 100% secure would almost certainly violate advertising laws. Second, presenting best-case results as typical performance is not allowed. If a product performs exceptionally well under ideal conditions, that outcome cannot be advertised as what most users should expect. This is especially relevant in areas like performance optimization, cybersecurity tools, or financial services. Third, misrepresenting products as all-natural, organic, or similar terms is tightly regulated. While this example often applies to food or health products, the same principle applies in technology. Labels and claims must be accurate and verifiable. Another major restriction involves health-related claims. Attributing medical or health benefits to a product without scientific or medical evidence is illegal in many jurisdictions. This is particularly relevant for wellness apps, fitness platforms, or health tracking software. Finally, the slide highlights a critical issue: presenting advertisements as informational content. This practice, sometimes called native advertising or dark patterns, can mislead users into thinking they are reading objective information when they are actually being marketed to. Regulators closely monitor this behavior. The key takeaway is that censorship and control in web applications are not just about blocking content. They are about ensuring accuracy, transparency, and consumer protection. Web developers, content creators, and organizations must understand these rules to avoid legal penalties, reputational damage, and loss of user trust. We're introducing the legal and regulatory framework that governs how data is protected on the internet and the web. To do that, we start with the concept of information security, often abbreviated as InfoSec. Information security is a broad umbrella term. It refers to all the methods, processes, and practices used to protect data throughout its entire life cycle, from the moment data is created to when it is stored, transmitted, used, and eventually deleted. This includes technical controls such as encryption, as well as administrative controls like policies and procedures. InfoSec also encompasses a wide range of data classifications. This includes private data such as personal information, proprietary and trade data such as business secrets, confidential data such as internal records, and regulated data such as financial or medical information. Organizations are expected to define how each type of data is protected and to regularly audit those protections. Another important point on this slide is that cybersecurity is a part of information security, not the other way around. Cybersecurity focuses specifically on protecting digital systems, networks, and online services from attacks. InfoSec is broader. It also includes physical security, human processes, and governance. For example, encrypting a database is a cybersecurity control, but defining who is allowed to access that database and under what conditions is an information security control. Here we also emphasizes that InfoSec and cybersecurity are not optional or purely technical decisions. They are constrained and guided by laws, regulations, and standards issued by local, state, national, and even international bodies. Governments, regulatory agencies, and trade organizations define minimum requirements for protecting data. For web application developers and organizations, this means security decisions must align with legal obligations. You cannot simply choose the level of security you want. You must meet regulatory expectations. Failure to do so can result in fines, legal action, loss of licenses, or reputational damage. The key takeaway from this slide is that web application security exists at the intersection of technology and law. Effective security requires understanding not just how to protect systems, but also why those protections are required under legal and regulatory frameworks. We're looking at a sampling of major information security and cybersecurity laws and guidelines in the United States. The key word here is sampling. This is not an exhaustive list, but it represents some of the most influential laws and frameworks that shape how organizations must design, secure, and manage web applications. The table is organized into 3 columns: the law or governing body, what it covers, and who it applies to. Understanding all 3 is critical because compliance is not universal. Different rules apply depending on the type of organization and the data being handled. Let's start with the California Consumer Privacy Act, or CCPA. This law focuses on privacy rights and consumer protection. Any business operating in California or doing business with California residents that collects personally identifiable information must comply. For web applications, this affects how user data is collected, stored, shared, and deleted. Features like privacy notices, opt-out mechanisms, and data access requests are not optional. They are legal requirements. Next is the Center for Internet Security, or CIS, controls. Unlike laws, CIS controls are guidelines, but they are widely adopted as best practices. They provide structured recommendations for protecting systems from cyber attacks, particularly in areas like configuration management, access control, and monitoring. Many organizations use CIS controls to demonstrate reasonable security, even when not legally required. The Children's Online Privacy Protection Act, or COPPA, regulates the online collection of personal information from children under the age of 13. This applies to any organization under U.S. authority, regardless of where the website is hosted. For web developers, this has direct implications for age verification, parental consent mechanisms, and data handling practices in apps or websites aimed at younger audiences. Next, we see COBIT, which stands for Control Objectives for Information and Related Technologies. COBIT is a governance framework, not a law. It helps organizations align IT operations with business goals while managing risk. COBIT is often used by larger organizations to ensure that security controls, policies, and audits are structured and measurable. Finally, we have FISMA, the Federal Information Security Modernization Act. This law applies to all federal agencies and requires them to protect their information systems. Any contractor or vendor building web applications for the federal government must also comply. FISMA heavily influences security requirements such as risk assessments, continuous monitoring, and compliance reporting. The big takeaway from this slide is that web application security is driven as much by law and governance as it is by technology. Developers and organizations must understand which laws apply to them and design systems accordingly. Ignoring these requirements can result in fines, lawsuits, loss of contracts, or regulatory enforcement actions. We continue our overview of major U.S. information security and cybersecurity laws and guidelines. As before, the goal is not memorization, but understanding when these apply and why they matter for web applications and organizations. We'll start with the Gramm-Leach-Bliley Act, or GLBA. GLBA applies to companies that offer financial products or services to individuals such as banks, lenders, and insurance providers. The core requirement is that organizations must secure the private information of customers. For web applications, this affects how financial data is stored, transmitted, and accessed. Strong encryption, access controls, and monitoring are not optional. They are legal obligations under GLBA. Next is HIPAA, the Health Insurance Portability and Accountability Act. HIPAA governs electronic health information and protects patient privacy. Any organization that handles healthcare data, including hospitals, clinics, insurance providers, and even third-party software vendors, must comply. In web applications, this means strict controls over authentication, logging, encryption, and data sharing. A misconfigured database or unsecured API can quickly become a serious HIPAA violation. Here we also list NIST, the National Institute of Standards and Technology. Unlike GLBA or HIPAA, NIST is not a law. Instead, it provides standards, guidelines, and best practices for managing cybersecurity risk. NIST frameworks are voluntary for most organizations, but they are widely adopted because they help demonstrate due diligence. Many laws and contracts reference NIST indirectly, making it extremely influential in how systems are designed and secured. Next is the Sarbanes-Oxley Act, or SOX. SOX requires U.S. public companies to retain financial records for at least 7 years and to maintain integrity and accountability in financial reporting. For web applications that handle financial data, this means implementing secure storage, access controls, audit logs, and tamper detection. Data loss or unauthorized modification can have serious legal consequences under SOX. Finally, we have FERPA, the Family Educational Rights and Privacy Act. FERPA protects student educational records and applies to post-secondary institutions. For colleges and universities, this directly impacts learning management systems, student portals, and advising tools. Web applications must ensure that only authorized users can access student records and that data is not improperly shared or exposed. The key takeaway from this slide and the previous one is that different laws apply to different types of data and organizations. Web application security is not one size fits all. Developers and organizations must understand which regulations apply to their systems and design security controls accordingly. Ignoring these requirements is not just a technical risk, it is a legal and institutional risk. We're introducing the red flags rule, which is a requirement enforced by the Federal Trade Commission, or FTC, along with other federal agencies. The purpose of this rule is to prevent identity theft, particularly in organizations that handle sensitive personal or financial information. The key idea behind the red flags rule is proactive detection. Rather than responding after identity theft has occurred, organizations are required to identify warning signs early and take action before harm happens. A red flag is defined as any questionable activity or behavior that could indicate identity theft. In the context of web applications, this is extremely relevant because most identity theft today begins online. For example, red flags might include repeated failed login attempts followed by a successful login from a new location, changes to account information immediately after login, multiple accounts being accessed from the same IP address, or requests to change contact or payment information that don't match a user's normal behavior. Individually, these events might not seem alarming, but together they can signal fraud. What makes the red flags rule especially important is that it requires organizations not only to recognize red flags, but to have a formal plan for how those red flags are handled. This means web applications must be designed with monitoring, logging, and alerting capabilities. Simply collecting data is not enough. The organization must actively look for suspicious patterns. From a web application security perspective, this rule connects directly to features like account monitoring, anomaly detection, multi-factor authentication triggers, and incident response workflows. If a system flags suspicious behavior but no one reviews it or responds, the organization may still be considered non-compliant. The red flags rule also reinforces that identity protection is not just an IT issue. It's a business and legal responsibility. Failure to implement reasonable detection and response measures can result in regulatory action, fines, and reputational damage. The key takeaway from this slide is that identity theft prevention is proactive, not reactive. Secure web applications must be designed to detect suspicious behavior, treat it seriously, and respond in a timely and documented way. Expanding on the red flags rule by outlining the 4 specific actions that must be included in an organization's identity theft prevention plan. These are not optional recommendations. They are required components of compliance. The first requirement is that the plan must include reasonable policies and methods for identifying red flags. The term reasonable is important here. It means the organization's policies should match the size, complexity, and risk level of its operations. For a web application, this might include identifying red flags such as unusual login patterns, repeated failed authentication attempts, unexpected account changes, or transactions that deviate from a user's normal behavior. The second requirement is that the plan must include procedures to detect those red flags. Identifying risks on paper is not enough. Organizations must implement technical and operational mechanisms to actively detect suspicious activity. In web applications, this often involves logging, monitoring, alerting systems, and automated triggers. If suspicious behavior occurs but no system is watching for it, the organization is not meeting this requirement. The third requirement focuses on response. The plan must include detailed descriptions of the actions the business will take when a red flag is discovered. This is where incident response comes into play. For example, actions might include temporarily locking an account, requiring additional authentication, notifying the user, escalating the issue to security staff, or conducting a fraud investigation. The key point is that responses must be defined in advance, not improvised after an incident occurs. The fourth and final requirement is that the plan must explain how the organization will keep its red flags current as technology and threats evolve. Identity theft techniques change constantly, especially in online environments. Web applications that rely on outdated detection methods quickly become vulnerable. This requirement emphasizes continuous improvement, regularly reviewing logs, updating detection rules, incorporating new threat intelligence, and adjusting controls as systems and user behavior change. Taken together, these four actions reinforce an important principle. Identity theft prevention is an ongoing process, not a one-time configuration. For web applications, compliance with the red flags rule depends on thoughtful design, active monitoring, and documented response procedures. The key takeaway from this slide is that having data is not enough. Organizations must actively watch for misuse, respond effectively, and adapt continuously to new threats. We're focusing on the General Data Protection Regulation, commonly known as GDPR. GDPR is one of the most influential data protection laws in the world, and it has reshaped how organizations design and manage web applications. At its core, GDPR establishes strict rules and guidelines for how personally identifiable information, PII, is collected, used, stored, and shared for citizens of the European Union. PII includes data such as names, email addresses, IP addresses, location data, and online identifiers. Under GDPR, this data belongs to the individual, not the organization collecting it. One of the most important aspects of GDPR is its extraterritorial scope. As the slide notes, GDPR applies to any website, regardless of where its servers are located, as long as an EU citizen interacts with it. This means GDPR is not limited to European companies. A website hosted in the United States, Asia, or anywhere else in the world may still be legally required to comply. The example on the slide illustrates this clearly. A social networking site with servers located in Texas must still follow GDPR requirements for any users who are EU citizens. Server location does not matter. User location and citizenship do. This is a critical concept that many organizations misunderstand. From a web application perspective, GDPR directly affects system design. Applications must support features such as clear consent notices, the ability for users to access and delete their data, limits on data retention, and safeguards against unauthorized access. Collecting data just in case is no longer acceptable under GDPR. GDPR also places strong emphasis on privacy by design and privacy by default. This means privacy protections should be built into the application from the beginning, not added later. Developers must think carefully about what data is truly necessary and how long it needs to be retained. The penalties for non-compliance are significant, including heavy fines and regulatory enforcement actions, but beyond penalties, GDPR has influenced global expectations around privacy and transparency. Many organizations now apply GDPR-style protections to all users, not just EU citizens. The key takeaway from this slide is that GDPR makes privacy a global concern. If your web application can be accessed by EU citizens, GDPR compliance is not optional. It is a legal requirement that directly shapes how data is handled and protected. We're breaking information security into two major categories that are especially important for web applications: application security and infrastructure security. While these areas are closely related, they focus on different layers of risk. We'll start with application security. Application security is focused on protecting web applications and APIs, the software layer that users interact with directly. This includes login systems, forms, APIs, databases connections, and business logic. Vulnerabilities at this layer often involve issues like insecure authentication, poor input validation, broken access control, or exposed APIs. A key point on this slide is that unsecured applications and API vulnerabilities can enable attackers to access other network elements and data. In other words, a weakness in a single web application can become an entry point into the broader system. For example, if an attacker exploits a vulnerable API endpoint, they may gain access to backend databases, internal services, or even administrative functions. This is why application security failures are often the starting point of major data breaches. Next, we move to infrastructure security, which focuses on protecting the systems and networks that support applications. This includes servers, workstations, mobile devices, cloud environments, and remote data centers. All of these components rely on the availability and proper functioning of an organization's communication network. Infrastructure security is critical because communication networks act as a conduit. If the network is compromised, attackers may move laterally between systems, intercept data, or disrupt services. Firewalls, network segmentation, secure configurations, and patch management are all examples of infrastructure security controls. The final bullet highlights an important cascading risk. If a vulnerability is exploited and a network segment fails, any systems that depend on that segment may also fail or become unavailable. For instance, if a core network switch or cloud region goes down due to an attack, multiple applications may stop working, even if the applications themselves are well designed. The key takeaway from this slide is that application security and infrastructure security must work together. A secure application running on an insecure infrastructure is still at risk, and a hardened infrastructure cannot protect a fundamentally insecure application. Effective information security requires addressing both layers simultaneously to protect data, systems, and users. We're focusing specifically on cloud security, which has become one of the most important and most misunderstood areas of information security. The first point is that a misconfigured cloud system is a target. This is critical. Many major cloud breaches do not happen because the cloud provider was hacked, but because customers misconfigured their cloud resources. Examples include publicly exposed storage buckets, overly permissive access controls, or unsecured APIs. Attackers actively scan the internet looking for these mistakes because they are often easy to exploit. The next point highlights a core concept in cloud security. Security is a shared responsibility between the subscriber and the provider. This means that cloud security is not something the provider handles entirely on its own, nor is it something the customer can ignore. The subscriber or customer is responsible for securing remote access to the system. This includes managing user accounts, enforcing strong authentication, configuring permissions correctly, protecting API keys, and ensuring that only authorized users and systems can access cloud resources. If weak passwords, exposed credentials or poor access controls are used, the cloud environment becomes vulnerable, even if the provider's infrastructure is secure. The cloud provider, on the other hand, is responsible for implementing security against penetration and data loss at the infrastructure level. This includes securing physical data centers, maintaining the underlying hardware, protecting the virtualization layer, and ensuring resilience against large-scale attacks. Providers like AWS, Microsoft Azure, and Google Cloud invest heavily in this layer of security. A common misconception is that moving to the cloud automatically makes systems secure. In reality, cloud platforms provide secure tools, but it is up to the subscriber to use them correctly. Misunderstanding this division of responsibility is one of the leading causes of cloud security incidents. The key takeaway from this slide is that cloud security depends on configuration, not location. A well-configured cloud system can be very secure, while a poorly configured one can be extremely vulnerable. Effective cloud security requires understanding exactly what the provider secures, what the subscriber secures, and how those responsibilities work together. We're shifting from laws and security concepts into practical risk mitigation. What organizations actually need to do to reduce risk in web applications and maintain compliance over time. The first point emphasizes administrative and employee workspace security measures. This is a reminder that security is not purely technical. Administrative controls include written security policies, defined roles and responsibilities, background checks where appropriate, and regular security awareness training. Employee workspace security might involve locked offices, badge access, clean desk policies, and restrictions on removable media. Many breaches begin with human error, so addressing this layer is essential. Next, the slide highlights the importance of installing firewalls. Firewalls act as a gatekeeper between trusted internal systems and untrusted external networks. For web applications, this often includes network firewalls, web application firewalls, WAFs, and cloud-based firewall services. These tools help filter malicious traffic, block unauthorized access attempts, and reduce exposure to common attacks such as scanning, brute force attempts, and denial of service activity. The third bullet focuses on maintaining documentation for security policies and systems. Documentation is often overlooked, but it is critical for both security and compliance. Organizations must be able to demonstrate what controls are in place, how systems are configured, and how incidents are handled. During audits or investigations, undocumented security measures may be treated as if they do not exist. The final point stresses the need to keep up with changes, modifications, and new requirements related to compliance and security. Laws evolve, technologies change, and attackers adapt. A web application that was compliant and secure 2 years ago may no longer meet current standards. This requires organizations to regularly review policies, update systems, apply patches, and monitor regulatory developments. The key takeaway from this slide is that risk mitigation is an ongoing process, not a one-time task. Effective web application security combines people, processes, and technology. Organizations that treat compliance and security as living systems rather than static checklists are far better positioned to protect their applications, data, and users over the long term. The payment card industry Data Security Standard, or PCI DSS, applies to any organization that processes, stores, or transmits credit card data. PCI DSS defines strict requirements for encryption, access control, monitoring, and testing. These requirements are designed to reduce fraud and protect cardholder data. Non-compliance can result in fines, loss of payment, processing privileges, and reputational damage. As a result, PCI DSS strongly influences how e-commerce web applications are designed and maintained. We continue our discussion of the Payment Card Industry Data Security Standard, or PCI DSS. PCI DSS applies to any organization that stores, processes, or transmits cardholder data, including online stores, subscription services, and web applications that accept credit or debit card payments. The table is organized into objectives on the left and specific requirements on the right. Together, these define what PCI compliance actually looks like in practice. The first objective is to build and maintain a secure network and systems. This is the foundation of PCI DSS. The first requirement under this objective is to install and maintain network security controls. For web applications, this includes firewalls, web application firewalls, network segmentation, and secure routing rules that limit exposure of cardholder environments. The second requirement is to apply secure configurations to all system components. This means systems should not run with default passwords, default services, or unnecessary open ports. Servers, databases, cloud resources, and payment systems must all be hardened to reduce attack surfaces. The next objective is to protect account data, which is the core purpose of PCI DSS. Requirement 3 focuses on protecting stored account data. This means card numbers should not be stored unless absolutely necessary, and if they are stored, they must be encrypted, masked, or tokenized. Storing full card numbers in plain text is a direct PCI violation. Requirement 4 addresses data in transit. Cardholder data must be protected with strong cryptography when transmitted over open or public networks, such as the Internet. In web applications, this means HTTPS, using modern TLS configurations. Any payment page or API endpoint handling card data must encrypt traffic end-to-end. The final objective shown on this slide is to maintain a vulnerability management program. Requirement 5 focuses on protecting systems from malicious software. This includes antivirus tools, malware detection, endpoint protection, and monitoring for suspicious activity across servers and workstations involved in payment processing. Requirement 6 emphasizes the need to develop and maintain secure systems and software. This directly impacts web application development. Organizations must apply security patches, fix known vulnerabilities, and follow secure coding practices. Vulnerable applications, even if the network is secure, can still lead to cardholder data breaches. The key takeaway from this slide is that PCI DSS is not just about encryption or firewalls. It requires a coordinated approach across network security, system configuration, data protection, and ongoing vulnerability management. Compliance is continuous, not a one-time checklist, and web applications are often at the center of PCI risk. We complete our overview of the Payment Card Industry Data Security Standard, or PCI DSS, by focusing on the remaining objectives and requirements. These controls emphasize access control, monitoring, testing, and governance, which are critical for protecting cardholder data over time. The first objective shown here is to implement strong access control measures. Requirement 7 states that organizations must restrict access to system components and cardholder data based on business need to know. In practice, this means users should only have access to the systems and data necessary to perform their job duties. For web applications, this involves role-based access control, least privilege permissions, and separating administrative functions from standard user access. Requirement 8 requires organizations to identify users and authenticate access to system components. This means every user must have a unique ID, no shared accounts, and authentication mechanisms must be strong. In web environments, this includes enforcing strong passwords, using multi-factor authentication for administrative access, and securing API credentials. Requirement 9 focuses on restricting physical access to cardholder data. While this may seem less relevant to web applications, it applies to servers, data centers, and even employee workstations. Physical access controls such as locked server rooms, badge access, and surveillance protect against insider threats and unauthorized data access. The next objective is to regularly monitor and test networks. Requirement 10 requires organizations to log and monitor all access to system components and cardholder data. Logging is essential for detecting suspicious behavior and investigating incidents. In web applications, this includes logging login attempts, API access, configuration changes, and transactions involving cardholder data. Requirement 11 emphasizes the need to test security regularly. This includes vulnerability scans, penetration testing, and configuration reviews. Security controls that are never tested may fail silently. Regular testing helps identify weaknesses before attackers do. The final objective shown on this slide is to maintain an information security policy. Requirement 12 states that organizations must support information security with organizational policies and programs. This is where governance comes into play. Technical controls alone are not sufficient. Organizations must have written policies, training programs, incident response plans, and clear accountability for security responsibilities. The key takeaway from this slide is that PCI DSS is a comprehensive, ongoing security program, not just a technical checklist. It requires strong access control, continuous monitoring, regular testing, and organizational commitment. For web applications that handle payment data, PCI compliance shapes how systems are designed, deployed, monitored, and managed every day. We're focusing on practical security actions that organizations can take to protect websites, starting with one of the most fundamental security controls, firewalls. A firewall can be either a hardware device or a software system that controls traffic flowing into and out of a network. Its primary purpose is to act as a gatekeeper, deciding which traffic is allowed and which traffic is blocked. For websites, firewalls are often the first line of defense against unauthorized access and malicious activity. Firewalls examine all incoming and outgoing traffic, allowing legitimate or friendly traffic while blocking traffic that appears suspicious or malicious. This includes attempts to exploit vulnerabilities, scan for open ports, or brute force login pages. Firewalls also track, monitor, and control traffic within sensitive areas of an organization's internal network, helping to prevent attackers from moving laterally if they gain access. Another important function of firewalls is access enforcement. Firewalls can block users or systems that do not have the correct security permissions, limiting exposure even if credentials are compromised. On the right side of the slide, we see key security measures associated with firewall use. One such measure is the use of demilitarized zones, or DMZs. A DMZ separates public-facing services, such as web servers, from internal systems like databases. This way, even if a public-facing server is compromised, the attacker does not gain direct access to internal resources. Maintaining network blueprints is another critical practice. Network diagrams document how systems are connected and where firewalls, servers, and sensitive data reside. Without accurate blueprints, Security teams may overlook exposure points or misconfigure firewall rules. Firewalls should also be configured to block unused ports and streamline protocol use. Every open port and unnecessary protocol increases the attack surface. By allowing only what is required, organizations reduce opportunities for exploitation. Regularly reviewing firewall configurations is essential. Over time, firewall rules accumulate, and outdated rules may introduce vulnerabilities. Periodic reviews help ensure that rules still align with business and security needs. Firewalls can also restrict database access, ensuring that databases are not directly exposed to the internet and are only accessible from authorized application servers. Another key practice is to verify wireless security, as poorly secured wireless networks can bypass perimeter defenses entirely. Organizations may also hide Internet Protocol or IP addresses using techniques such as network address translation or reverse proxies. This makes it harder for attackers to directly target internal systems. Finally, the slide emphasizes the importance of host-based firewalls, which operate directly on individual servers or workstations. These provide an additional layer of protection even if network-level defenses are breached. The key takeaway from this slide is that firewalls are not just a single device or rule set. They are part of a layered defense strategy that includes segmentation, monitoring, configuration management, and continuous review. When implemented correctly, firewalls significantly reduce the risk of website compromise. We're looking at a demilitarized zone, or DMZ, positioned behind a firewall. This diagram illustrates how organizations safely expose public services, like websites, while protecting internal systems. Let's start on the right side of the diagram with the internet. This represents all untrusted external traffic: users, automated scanners, bots, and potential attackers. Because the internet is untrusted, traffic from this side must be carefully filtered before it reaches any internal resources. Moving left, the first security control we encounter is a firewall. This firewall enforces rules about what traffic is allowed in and out. Typically, only specific ports and protocols, such as HTTPS on port 443, are permitted. Everything else is blocked by default. This deny by default approach is fundamental to perimeter security. Next, we see traffic routed toward the DMZ. The DMZ is a separate network segment designed specifically for systems that must be accessible from the internet. In this diagram, the www server is placed in the DMZ. This server hosts the public-facing website, meaning users on the internet can reach it, but only under tightly controlled conditions. The key idea here is containment. If the web server is compromised, the attacker gains access only to the DMZ, not to the internal network. This dramatically limits the damage that can be done. Now look at the internal firewall between the DMZ and the internal network. This firewall is even more restrictive than the perimeter firewall. It typically allows only specific one-directional communication, such as the web server querying a database or application service. Direct access from the internet to internal systems is never allowed. At the center of the diagram, we see a routing or switching device, which manages traffic between network segments. This device enforces segmentation, ensuring that traffic follows approved paths and cannot bypass security controls. Finally, on the left side, we see the internal network. This is where sensitive systems reside: databases, internal applications, administrative tools, and employee resources. These systems are never directly exposed to the internet. Even users accessing the website do not interact with internal systems directly. They interact only with the DMZ. The arrows in this diagram are important. They show that traffic flows are intentional and controlled, not open or implicit. Every allowed path exists for a specific business purpose. The key takeaway from this slide is that a DMZ acts as a security buffer. It allows organizations to provide public services while minimizing risk to internal systems. A properly designed DMZ assumes that public-facing systems may be compromised and plans for that reality by limiting what attackers can reach. In modern environments, this same concept applies whether systems are on premises or in the cloud. DMZs may be implemented using virtual networks, security groups, and routing rules, but the principle remains the same: segmentation, least privilege, and controlled access. Continues our discussion of practical security actions organizations should take to protect websites, focusing on password configuration and protecting stored personally identifiable information, or PII. We'll start with configuring passwords and settings. One of the most common and most preventable security failures is leaving vendor-supplied default passwords or settings unchanged. Many attackers rely on these defaults because they are well documented and easy to exploit. As a result, organizations must change all default passwords and review security settings during the installation of every component, including web servers, databases, content management systems, routers, and cloud services. Beyond simply changing passwords, secure configuration includes disabling unnecessary services, enforcing strong password policies, and limiting administrative access. Secure defaults do not happen automatically. They must be deliberately implemented. The second major focus of this slide is protecting stored PII data. Any data that can identify an individual, such as names, email addresses, financial information, or authentication credentials, must be protected against unauthorized access and disclosure. The first protection method listed is to apply strong encryption. Encryption ensures that even if attackers gain access to stored data, the information remains unreadable without the proper keys. This applies to databases, backups, logs, and cloud storage. The slide also emphasizes that sensitive payment card data, such as magnetic stripe data, RFID chip data, and verification codes like PINs or security codes, should be stored only when absolutely required. Many security standards, including PCI DSS, explicitly prohibit storing certain types of card data after authorization. Storing unnecessary sensitive data dramatically increases legal and security risk. Finally, the slide highlights the importance of the principle of least privilege. This principle states that users and systems should have only the minimum level of access needed to perform their tasks. In practice, this often means implementing role-based access control, where access to data is determined by job role rather than individual discretion. The key takeaway from this slide is that data protection begins with disciplined configuration and access control. Strong passwords, secure defaults, encryption, and limited access work together to reduce the impact of both external attacks and insider threats. These actions are foundational to nearly every security framework and compliance standard. Our discussion of security actions used to protect websites, with a focus on protecting data in transit, defending against malware, and keeping systems up to date. These controls work together to reduce both external and internal security risks. We'll begin with encrypting the transmission of data across open public networks. Anytime data travels across the internet, whether it's login credentials, personal information, or payment details, it is potentially exposed to interception. Without encryption, attackers can eavesdrop on communications using techniques like packet sniffing or man-in-the-middle attacks. To secure data in transit, organizations must use encryption protocols, most commonly HTTPS with modern TLS configurations. This ensures that even if traffic is intercepted, the data remains unreadable. Secure transmission is not optional. It is a baseline requirement in nearly every security and compliance framework. The slide also emphasizes securing wireless communications. Public or poorly secured wireless networks are especially vulnerable to interception. Organizations must enforce strong wireless encryption standards and avoid transmitting sensitive data over insecure connections. In addition, organizations should monitor communications and protocols. This means watching for unusual traffic patterns, deprecated or insecure protocols, and unexpected connections. Monitoring helps identify misconfigurations and potential attacks before damage occurs. Next, the slide highlights the importance of using and regularly updating antivirus software. While antivirus alone cannot stop all attacks, it plays an important role in detecting known malware, ransomware, and malicious files. Protecting the system that hosts a website helps protect both visitors and the organization itself. If a server is compromised, attackers may distribute malware to users or steal sensitive data. Antivirus software must be kept up to date. Outdated antivirus tools are far less effective because they cannot detect newer threats. This applies not only to servers, but also to administrative workstations used to manage websites. Finally, the slide addresses one of the most critical and most frequently neglected security practices: regularly updating and patching systems. Many successful cyber attacks exploit known vulnerabilities for which patches already exist. Continuous updates and routine maintenance significantly reduce the attack surface. Patching should be tested and evaluated, especially in production environments, to ensure updates do not break functionality. However, when patches address confirmed security vulnerabilities, they should be applied as quickly as possible. Delaying security patches gives attackers a window of opportunity. The key takeaway from this slide is that security is not static. Encrypting data, defending against malware, and applying patches are ongoing responsibilities. Organizations that fail to maintain these basics often fall victim to preventable attacks. Strong website security depends on consistent monitoring, timely updates, and disciplined operational practices. Focuses on an often overlooked but critically important area of security: restricting physical access to the workplace and to data. While we often think of cyber attacks as purely digital, many security breaches begin with physical access to systems, devices, or infrastructure. The first recommendation is to use facility access controls to monitor and limit who can physically reach systems that store, process, or transmit sensitive data. This includes technologies such as badge readers, keycard systems, biometric scanners, or even traditional locks and keys. These controls help ensure that only authorized personnel can access server rooms, networking closets, or data storage areas. A real-world example of this would be a company that allows unrestricted access to its server room. If an unauthorized person can walk in and connect a USB device, steal a hard drive, or reset hardware, digital security controls become meaningless. Physical access is often the fastest way to bypass cybersecurity defenses. Next, organizations are advised to use cameras to monitor data-sensitive areas and to retain recordings for a defined period, typically at least 3 months unless restricted by law. Video surveillance acts as both a deterrent and an investigative tool. If an incident occurs, recorded footage can help identify when access occurred, who was present, and what actions were taken. The slide also emphasizes restricting physical access to wireless access points, gateways, hard drives, and handheld devices. These components are especially vulnerable because they can be tampered with, removed, or replaced. For example, an attacker could install a rogue wireless access point or physically remove a hard drive containing sensitive data. Another key point is restricting access to backups that contain sensitive data. Backups are frequently targeted because they often contain large volumes of unencrypted or lightly protected information. Best practice is to store backups in verified, secured off-site locations that follow strict access control and audit procedures. Finally, organizations must develop procedures to clearly distinguish between employees and visitors. This includes visible badges, visitor sign-in processes, escorts, and employee training. Social engineering attacks often rely on attackers pretending to belong. If staff cannot easily identify who should and should not be present, physical security breaks down quickly. The key takeaway from this slide is that physical security is foundational to cybersecurity. No amount of encryption, firewalls, or access controls can fully protect data if attackers can physically reach systems. Effective website and data protection requires aligning physical, administrative, and technical controls into a single, cohesive security strategy. Two critical defensive practices in website security: logging and log management, and vulnerability scanning and penetration testing. Together, these controls help organizations both detect attacks and identify weaknesses before attackers do. We'll start with implementing logging and log management. Logging involves collecting and monitoring log files generated by an operating system, web server, database, and applications running on a server. These logs can reveal valuable information such as intrusion attempts, repeated login failures, unauthorized access to protected data, configuration changes, and abnormal system behavior. In many cases, logs provide the first indication that a security incident has occurred. For example, a spike in failed login attempts may indicate a brute force attack, while access logs may show an account accessing data it should not normally reach. Logging also allows an organization to track all user activity within a system. This is essential for accountability, auditing, and compliance with regulations such as PCI DSS, HIPAA, and GDPR. Without proper logging, it is extremely difficult to prove what happened during a breach or to meet legal reporting requirements. One of the most important benefits of logging is incident reconstruction. Log data can help determine where a problem occurred, when it occurred, and who was involved. In other words, logs help answer the questions investigators always ask. What happened? When did it happen? How did it happen? And who was responsible? However, logging is only effective if logs are actually reviewed, protected from tampering, and stored securely. Logs that no one monitors or that attackers can erase provide little real security value. The second major focus of this slide is conducting vulnerability scans and penetration tests. Organizations should perform regular vulnerability scans of both internal and external networks. These scans help identify missing patches, insecure configurations, outdated software, and unauthorized devices, including newer rogue wireless access points. The slide emphasizes conducting quarterly and annual testing, which aligns with industry standards and compliance requirements. In addition, systems should be rescanned after changes, such as new hardware installations, major upgrades, or configuration modifications. Vulnerability scanning identifies potential weaknesses, but penetration testing goes a step further. Penetration testing simulates real-world attacks to determine whether vulnerabilities can actually be exploited. This testing should be performed at least once per year, or after significant infrastructure or application changes. Penetration testing helps organizations understand their true risk exposure. A vulnerability that looks minor on paper may allow full system compromise in practice, while others may be low risk due to existing controls. Finally, scan and test results must lead to action. Identified vulnerabilities should be prioritized, system upgrades installed, and patches applied promptly. Security testing without remediation creates a false sense of safety. The key takeaway from this slide is that security is an ongoing process, not a one-time setup. Logging helps detect and investigate attacks, while scanning and testing help prevent them. Together, these practices form a continuous feedback loop that strengthens website security over time. Highlights a part of cybersecurity that is often underestimated, but absolutely essential: documentation and risk assessments. While technical controls like firewalls and encryption protect systems, documentation and training protect the people and processes behind those systems. We'll start with information security policies. An information security policy is a written management-approved document that defines how an organization protects its information assets. This policy applies not only to employees, but also to contractors, vendors, and even visitors who may interact with systems or data. The policy clearly communicates what is allowed, what is prohibited, and what responsibilities each individual has when handling information. Without a written policy, security expectations are vague, inconsistent, and difficult to enforce. For example, a security policy may define rules for password creation, remote access, acceptable use of company devices, data classification, and incident reporting. When an incident occurs, the policy serves as a reference point for determining whether procedures were followed or violated. Another key role of documentation is accountability. Policies establish that security is not optional or informal. It is an organizational requirement backed by leadership. This is especially important for regulatory compliance, audits, and legal investigations. The slide also emphasizes that documentation lets employees know what is expected of them regarding information security. This reduces confusion and lowers the risk of accidental violations, such as employees storing sensitive data in unapproved cloud services or sharing credentials. However, documentation alone is not enough. Policies that sit unread in a shared folder do little to improve security. That is why the final bullet stresses security awareness training. Employers should provide regular security awareness training so employees understand real-world threats and how their actions affect organizational security. Training helps employees recognize phishing emails, social engineering attempts, unsafe downloads, and improper data handling. For example, a well-trained employee is more likely to question a suspicious email asking for login credentials rather than clicking a malicious link. In many breaches, the initial point of compromise is a human error, not a technical failure. Risk assessments tie all of this together. A risk assessment evaluates what assets need protection, what threats exist, how likely those threats are, and what impact a successful attack would have. These assessments help organizations prioritize controls and allocate resources effectively. In short, documentation and training turn security from a technical problem into an organizational culture. When employees understand the rules, recognize threats, and know how to respond, security becomes proactive rather than reactive. The key takeaway from this slide is simple but powerful. Strong cybersecurity depends just as much on people and policies as it does on technology. In this module, we explored the core concepts behind web applications and their security, moving from how web applications function to how they can be designed, protected, and maintained in a secure and compliant way. We began by examining how a web application functions, including how users interact with web servers, databases, and application logic. Understanding this flow is essential because every interaction point, whether it's a login form, API request, or data submission, represents a potential security risk if not properly designed. Next, we reviewed standards for web applications, including security frameworks, regulatory requirements, and industry best practices. These standards provide consistency, accountability, and guidance for developers and organizations, helping ensure that applications meet legal, ethical, and technical expectations. We then focus on how to design and build a secure and compliant web application and website. This included secure configurations, encryption, access controls, logging, patching, and documentation. Secure design is not something added at the end. It must be integrated throughout the development and deployment lifecycle. Finally, we discussed best practices to mitigate risks for websites and web applications. These practices included using firewalls, implementing DMZs, securing data at rest and in transit, performing vulnerability scans and penetration testing, restricting physical and logical access, and maintaining strong security policies and user training programs. The key takeaway from this module is that web application security is not just a technical challenge. It is an organizational responsibility. Secure systems depend on well-designed technology, informed users, documented processes, and continuous risk assessment. By understanding both how web applications work and how they can be protected, you are better prepared to evaluate real-world systems, recognize vulnerabilities, and apply security best practices in academic, professional, and industry settings. Alright, that concludes this video lecture for this chapter. If there's any questions, thoughts, concerns, or issues, please don't hesitate. Feel free to reach out. Thank you.